Today we are going to discuss about yield point phenomena. Uh, all of us must know that exceptions to the rule are always very interesting. And if you look at the anomalies in stress strain curves for mild steel or light materials or metallic systems, it really has potential to meet the curiosity of technology scientists or engineers. So it is you can tell that it is a deviation from the normal or general trend of stress strain curves, and it seems mainly mild steel or like kind of metallic system or alloys. So suppose mild steel, if you deformed in higher tension, or you can tell the perform tensile strength in the mild steel, it is found that the stress strain curve is not at all smooth, whereas it actually shows some marked irregularities with negative slope occurring at or near the initial yield point yield of the curve. So for that, if you want to see next slide, we can look at the picture, then we can understand what I want to convey. So in this stress strain curve, we can observe that it is not at all smooth, and there is certain kind of irregularities are there, and you can see the negative slopes occurring at or near the initial yielding process of the curve. So the actual shape of stress strain curve is, you can tell that it's dependent to some extent on the type and characteristics of the tensile testing meshing used. Also, it depends upon the material, how it reacting that. So if you can take the example of mild steel, then the progress of deformation you can divide into three stages. If you look at the picture, then you can easily understand what are the different that three stages are. The normal elastic extension, that is marked AB, capital AB, is terminated at the stress level known as upper yield stress, marked as a sigma suffix U. And deformation then proceeds at a decreased stress level known as the lower yield stress, that sigma suffix or superscript L. Superscript L, sigma superscript L, that actually representing the lower yield stress or lower yield point. But the deformation at this stage is not homogeneous. What you understand? The specimen is divided into a region, and you can see that regions can create a Luder bands. Later on, we'll understand what does mean by Luder bands. In that Luder band region, where the strain has the value, you can see in the plot given in the slide that epsilon suffix or superscript capital L, and other regions which are not yet deformed is, you can tell that those are with the zero strain. So these bands are also known as Hartmann lines, Hartmann-LINES, Hartmann lines, and or somebody also named as stretcher strains. So this kind of Luder band strain can in steel be as high around 5%. So dependent on the grain size, the deformed region on a test specimen, you can see that it clearly can be shown that different condition of critical illustration. Suppose Luder band of steel strip will be different. So it is also looked at the dependent on the different size shape of the specimen. So now we are going to concentrate on the lower yield stress. So at the lower yield stress, what will happen? Deformation proceeds by a growth of loader bands which spread along the specimen until at the point D, capital D marked is that point it reached. The entire surface of the stress specimen is covered by the loader bands and all areas of the test length have been strained by an amount presenting in the picture, that is epsilon superscript capital L. So if you go beyond the point D, means if you go beyond the lower end point lying that this point from D to ultimate tensile stress, that is point capital E, or you can mark as a point capital E, that is UTS, ultimate tensile stress. The deformation is essentially homogeneous. So D2U part, if you look at the stress strain plot, deformation is homogeneous, but whereas you can previously know that C to D or beforehand B to D, you can tell that deformation is not homogeneous. So these deformation is essentially homogeneous, and after that necking develops. I will discuss when we will discuss the fracture, what is necking, what is the criteria of necking. But necking, now for the time being, you remember like that. There is a reduction in the thickness of the material at a certain distance, and the fracture slowly going to be happen. The fracture going to be happen. So leading to a normal ductile fracture. Necking actually leading to a normal ductile fracture in case of this mild steel example we have taken. And at the point capital F is marked to indicate that at that point normal ductile fracture is going to occur. So as we will see, will be seen that there are numerous variants of this stress strain curve dependent on the material, temperature, grain size, other metallurgical variables like strain rate and all those things. All are going to influence the stress strain plot. So the technological importance of yield point is great. Why it is so important or significant, the yield point? Because it actually tells you when in the service condition what load the material going to start to fail, or when the plastic deformation starts. So in pressed mild steel component, for example, the loader band may lead to certain marking resulting from inhomogeneous deformation. Already we understood at that B to D section there will be a inhomogeneous deformation, and that creates certain mark in the surface of the specimen or mark in the resulting certain marking system, marking line, and these are commonly known as stretcher strains. Again, I am repeating, the loader bands sometimes lead to, not sometimes, always lead to markings resulting from the inhomogeneous deformation, and these are very commonly or usually known as stretcher strains.
So what does the EL?
What
Sir,
does the
can you please again tell about the epsilon L stands for?
that is the strain up to the lower yield point, that is epsilon superscript capital L. So that part, that can, some material that can be up to 5% is a very huge, and there you can see the loader band and stretcher strains.
Okay, sir.
So now we are going to understand, okay, we know that certain problem with the material, certain material have different features with respect to stress strain behavior, but also you should know that is the effect of tensile meshing and specimen stiffness on the stress strain plot is very significant. That part also we should be aware. So before you can start to study the yield point phenomena, we should know that. So what we know, before studying the yield point phenomena, any further we want, it is very much necessary to dispose of two elementary facts. But it is very important aspect of measurement of yield points and the effects of tensile machine and specimen stiffness. So there are two kind of tensile machine we will come across in future. One is soft and one is hard machine. So for the soft machine, the load is considered connected to the specimen by soft spring, so that if the specimen yields suddenly, the load is virtually unaffected, or it is not going to be influenced by the suddenly if you change the load. So it is not going to happen. So dead weight loading, hydraulic machine, pivoted beam type tensile machine, you can tell that those things are come into this category as shown in the picture also. But if you go for other kind of machine, that is hard machine, some allowances can be made by noting the drop in the beam as the yield point is reached. But rapid changes in load such as is found that mild state at elevated temperature, these are the limited value. Means that if you suddenly change the load or sometimes, those have limited impact where the loading arrangement is connected to specimen through a hard spring. So for accurate measurement and to follow the rapid and also to follow the rapid changes in the load, hard machine are necessary. Here the load is measured and transmitted to the specimen by a load cell and strip member. So what will happen? You must know that therefore there will be a very small sudden elongation in the specimen, result in a large drop in load. So these are the futuristic behavior of tensile machine. It's a nitty-gritty of that. So we know now what will be the takeaway from last 1 minute discussion, that there should be an arrangement, the two-way arrangement. One is soft spring attachment and another is load cell and strip members. One is hard type of tensile machine and soft type of tensile machine. And based on that, they are going to have an impact on the stress strain plot also. So the effects of machine rigidity can be very simply illustrated if you look at the picture. The tensile specimen in this imagine to have a Young modulus capital E, and the machine and supporting members have a effective springs constant K. So under a particular load capital A, the extension of the system you can easily write capital L by K plus L into small l, that is the specimen length, by A into capital E, A cross section of the specimen, and capital E already we know. And based on that, if you see the extension of this specimen, then the elastic parameter of machine will also have a, other than that, the elastic parameter of the machine will also have an influence on the magnitude of the yield point drop. So if the effective stiffness of the machine decreases the load relaxation, and so what will happen? If the effective stiffness of the machine decreases, the load relaxation also decreases. So what will imply? You will become less abrupt. If you look at the picture, only rounded yield is going to be seen. So here you can say that the stress barely falls below the nucleation stress, as so the Luder bands will be forced through the specimen at much higher velocity, and that actually show the effect of axial loading on the magnitude of yield drop. Here also you can see in the picture the effect of spring constant, K on stress strain plot, or elastic elements of tensile machine, how the spring is loaded, and based on the different spring constant, the stress strain plot just in the area of yield point, it is going to be changed. So that is also one thing when you are going to perform these kind of things, tensile testing, and you should remember that effect of tensile machine also important. So one should very careful in order to understand, is it material property itself or there is any influence of tensile machine on the stress strain plot. Here is a single crystal copper and their stress strain plot is shown, and I just want to bring to your notice that there is a discontinuous slip you can see, and discontinuous slip also may cause a serration in stress strain plot. Okay.
So why does discontinuous sleep happen, sir?
When there is a dislocation, mobility is hampered due to spile up or other sessile dislocation is there. So sleep is not continuously stop. And again, certain stress is coming and help to reach the pulse nervous stress or the movement of the dislocation stress required for that. That required stress is coming from the external agency, maybe in the form of load or force, then again the sleep occurs. So that's why the discontinuous is not continuously sleep is going to occur. So what will happen? Then you will see the sleep steps much more evidently. That is one of the reason. Now we are going to discuss about the effect of initial density of mobile dislocation on yield point. Mobile dislocation is more. So if you look at the picture at A, 10 to the power 6 means the dislocation density is lower. So with respect to further B, C, D, E cases. And as the dislocation density increases, a mobile dislocation density increases, what is happening? The upper yield point is lowering and it slowly reaches to the lower yield point. That is very interesting phenomena. And that regarding this discussion, lot of reasons are there, but still people are working on that. And acoustic simulation perspective also, we are also looking at that. So that very macro scale, the reason is like that. The dislocation density is lowering, mobile dislocation means ductility is less. So all kind of discontinuous sleep and all those things are really not much with respect to resolved shear stress, because resolved shear stress also going to decrease because the uh, Smith factor is slowly deviate from its maximum value. That is the argument, but this argument is still not so evident, so strong. So now we can that the dislocation, mobile dislocation density is decreasing, and based on that you can check that the resolved shear stress is also falling down. That you have to remember. This is a fact. The reason we have to find out is it's typical. It's not so clear area. It's a little bit of gray area till yet. Stress strain plot of polycrystalline mindset. That part we are going to understand now. If you look at the picture, so that is based on the temperature. If you look at the picture, when the temperature is increasing, the slowly the stress strain plot is shifted downwards. And certain temperature, up to certain temperature, from at lower temperature the sedation is less, and when it goes slowly high temperature, you are getting the amplitude of the sedation, or that kind of yield point fluctuation is much more higher, you can tell. So these are the observation, and reason most probably the when high temperature the dislocation in behavior based on the climb and all those processes activated. So dislocation pinning, unpinning, dislocation annihilation, those are operative. But if you go beyond certain temperature, then also the sedation range, you can tell the epsilon L, that is the part where that strain, where the sedation of the yield stress strain plot are there, that also shrinked, reduced. If you look at 2236, those are also maybe the reason of more climb is occurring. So after certain time, the strain hardening, then steel point is enhancing, and after that UTS is raised, and then it are not going to carry the load, it is going to be fractured. This is the scenario. Still, these area, the yield point phenomena, sedation for material to material and those things, the underlying mechanism still is not so clear cut. It is there, some interstitial or defect, interstitial atom and defect interaction for mild steel, people used to argue, but still is not so clear. So it required lot of study and research. But these are the phenomena is fact, and we are saying that my job is to just show the fact and try to understand, try to explain that there is the underlying physics related to interstitial defect interaction, or maybe the temperature strain rate sensitivity. But clear concept we have to find, because it's not there. So certain atomistic simulation or maybe require certain experimental demonstration is not so sufficient logic, or clear logic is not there. Stress strain plot is a different elongation as different Cohen sample, age sample, how things are happening. It's just I have given, it's not so important. You can skip it. This is the thing. Variation upper and lower stress with a grain size. The upper and lower, both, one is very important, both are following the Hall-Patch equation. That is initial yield point in stress plus K, the constant, and D to the power, D is the grain size, grain diameter to the power minus half. So the lower the grain size or finer the grain, the strength would be high. That you can see. But this is true for both upper yield point yield stress and lower yield stress. That is very good thing, because then only you can understand how grain size can enhance the strength of a particular grain size. Decreasing grain size or finer grain size can enhance the strength of a metallic system. That you can easily understand. This is very important equation. This is Hall-Patch equation. One should remember this. And another way explain that delay times of a mild steel varying grain size. So if you look at the picture, these are the experimental study carried out by Russell and its group. Here you can see the the delay T0 exp sigma y sigma c, sigma c, not sigma c, sigma 0, the initial yield point and that particular yield stress. Then you can see that delay time if you see in the x-axis. So the grain diameter. So grain diameter, when the grain diameter is lower, when finer grain, you can see the uh, with respect to when it is a delay, the stress is required to be more. So yield stress is increasing, but delay in the fracture is not so high. Delay fracture is seen for the higher grain size, but yield strength will be lower. So this is the very important thing. When you reach that yield stress point, do you want to stronger material, then maybe you go for finer grain size, but you may have a problem that it actually reduces the delay of the fracture occurrence. So that is a trade-off kind of things. You have to optimize, you have to take two conflicting objectives based on the grain size and delay of the fracture as well as the strength. Then you have to find out as per the required service condition. So this is the formula for delay, and this is just one example that the same activation energy applies to the propagation rate of Lunar band. If you look at this, if you want to note that if the in this alloy E equal to 6.8 kilocalorie per mole, and same kind of activation energy also applies to propagation rate of the Lunar bands. So moral of the story of this is, what will be the takeaway, that whenever you want to know the yield point phenomena, first you have to understand that it is a inhomogeneous, or it kind of is not homogeneous deformation. It is a not, it is at all not a homogeneous deformation. So when it is not a homogeneous deformation, so that certain kind of Lunar band region or stress strain region, you can see the fluctuation of a stress in a particular strain age region, and that can be marked as epsilon capital A, lower yield stress region. Time delay, and then you find out the activation energy barrier that is quite related to propagation rate, activation energy area, activation energy barrier related to propagation rate of Lunar bands. They are related. That is very interesting thing. But today class, what I am expecting from you, only you should remember what is the stretcher strain reason, how upper yield point is defined, lower yield point defined. I have taken lot of example which is not directly involved, but you can see certain what can be the different features of stress strain plot, that you can understand it. There are a lot of anomalies in stress strain plot that you can uh, conceptualize, and now people are still working on that, find out the reason for those anomalies in the stress strain plot, and between upper yield point and lower yield point are variation of the yield strength value, and the fluctuation is known as yield point phenomena. It is a very burning topic. People are really doing research nowadays in different scale, in nano scale, in macro scale, in micron scale, in meso scale. People are working to understand why this is happening, and for different other factors, temperature of deformation, strain rate, material properties, tensile test machines, springs constant, and all those things, how are important, how they are important variable with respect to defining yield point phenomena. People are working. So you should remember, if somebody will ask what is yield point phenomena, you should explain based on the variation in upper yield point and lower yield point and the background, and then try to explain the stretcher strain and Lunar band concept. That's all. But I have discussed, I have given a lot of pictures so that you can understand that variation with respect to normal stress strain plot are very not so scarce. Lot of metallic systems are exhibiting such features. Thank you.
Sir, you have said that if we have the fine grained structure, we have the delay in fracture time.
No, I did not say that. Fine grain structure, the strength will be high, but delay in fracture will be coarser grain. If you look at this picture, so there is a trade-off. I told that is a conflicting objective is there.
Okay, sir. Sorry for my misconception.
Next week is a offline or online classes, na?
Yes, sir. Next week it is online. Next to next week will be offline, sir.
Very good. And when all of you are coming, how many have come back? 4 of you have come back?
Sir, I am Rourkela only, sir. I am always in Rourkela only.
Okay, okay. So, Abhay? Abhay,
Sir, I will be coming on 20, sir.
20. Then Snigdha, Saurabh.
Yes, sir.
When you are coming back?
Sir, within 2-3 days I will be back, sir.
You are from?
Sir, Jamshedpur, Jharkhand.
Oh, fast. Ashish Tiwari? Ashish Tiwari? Omkita Chaudhary?
Yes, sir. Sir, by 18 I will reach, sir, in Rourkela, sir.
Okay. I just taking the sample. How? Alayal Samuel,
Yes, sir.
when you are reaching to Rourkela?
21st on.
Okay. Neeraj Kumar? Neeraj? Shudiksha? Shudiksha, are you there? Neeraj? Nobody is responding. Shubhodip,
Yes, sir. Yes, sir.
when you are reaching?
Around 20.
So I think all of you have to reach by 23rd.
Yes, sir.
Okay. Okay, then I am closing the meeting. Next week will be the online. Next week will be the online, and after starting of the offline class, first class will be the class test.
Yes, sir. Okay, sir. Thank you, sir.